Right, so in this video, we're going to have a look at curly arrows, but just curly arrows in general, as opposed to looking at the specific mechanisms that we've studied. We do only have to study 5 different types of reaction mechanisms, and I mean, essentially you can learn those ones off by heart. But what they can do in the exam is they can give you unseen mechanisms, and they can ask you to fill in the arrows if they give you the products, or they could also give you a situation where they've drawn the arrows and they ask you to draw the product. So you do need to be able to, you need to understand the curly arrows. And it will massively help you with the reaction mechanisms that you do need to know if you actually understand why the product is the product, as opposed to just learning it off by heart. So I'm going to go through a number of different examples. It's really important in this video, even more so than in all of the others, that when I say press pause and have a go, that you actually do. When I go through all the examples, once I've done it and given you the answer, it might be quite logical. But it's really important that you can do it by yourself without having seen the answer first. So really, really important that you have pen and paper in front of you for this video, and that you're pressing pause and actually doing the questions, because there's loads of them, but they only take a couple of seconds each. So the first example I'm going to have a look at here is using the electrons in a lone pair. Okay, so I've got NH3 here with a lone pair, and I have a curly arrow going from the NH3 to a H+. Okay, kind of common mistake is to interpret that as the nitrogen is giving 2 electrons to the hydrogen, and both of those electrons are leaving the nitrogen and going to the hydrogen. Okay, if you did that and nitrogen gave both of its electrons away, it would have a +2 charge on that nitrogen, incredibly unstable. Hydrogen would gain 2 electrons, so if it gained 1, it would be neutral. Gaining 2 gives it a -1 charge. So I've got 2 really reactive charged species. Like, that's never going to happen. So when you see this arrow going from a lone pair to another atom, be it with a positive charge or even with a delta positive charge, what that's telling you is that you're using the electrons to create a new bond between those 2 atoms. So instead of getting this as my product, I'm actually going to get this. So nitrogen is still bonded to the same 3 hydrogens it was before, but now it's got a 4th hydrogen. And those red electrons there that I've highlighted are used to form that new bond. We've seen these types of bonds before. They're called dative covalent bonds. It's when one atom contributes both electrons to the covalent bond. And it's really important then you can put in your charges. So if we're starting with something positive, that charge is not just going to go away. You need to end with something positive. Because nitrogen contributes both electrons to that bond, it is essentially losing electron. If you think of your normal covalent bond, hydrogen would give 1, nitrogen would give 1 too, so they're sharing evenly. Here, nitrogen gives both electrons to that bond. Hydrogen contributes nothing. Nitrogen effectively loses an electron and has a positive charge. So I want you to have a go now at doing, just do this, ignore these ones. Just do that first one. Press pause and have a go at just doing that first question. All right, so this is what you should have had for your answer. Again, oxygen is not giving hydrogen both of those electrons. Instead, it's forming a bond with hydrogen. So oxygen is still bonded to the carbon chain as it was before. It's still bonded to 1 hydrogen. I've just drawn that there. You don't need to show the bond. And then I've now got oxygen bonded to a 2nd hydrogen, which it wasn't bonded to before. And you'll see the electrons that I had there in the lone pair are the electrons that are being used to form that covalent bond. Again, if I start with something positive, I need to have a positive product. And again, it's going to be on the oxygen because it gives both electrons to that covalent bond. All right, have a go at this one. So again, press pause and have a go. This one, I mean, it looks a little bit harder, but it is exactly the same. Again, nitrogen is going to use those electrons to form a new bond with this carbon, the carbocation with the positive charge. So everything is still bonded to nitrogen as it was before. You still got that carbon chain, you still got the 2 hydrogen atoms, but now nitrogen is using those electrons to form a new bond with this carbon. Really important that you've got the right number of carbons. All right, if I call that one carbon number 1, there it is there, carbon number 1. And carbon number 1 is bonded to 1, 2, 3 methyl groups. Make sure you've got 1, 2, 3 methyl groups in your product. You should have 4 carbons, just as I had here. Again, that positive charge is going to go from the carbon to the nitrogen because nitrogen gives both electrons to that bond. I have got another 2. So for this one, press pause and have a go at doing both of them. So if you go through the first one, same as the one above it, okay? Except this time there's an important difference. This time I'm starting off with oxygen with a negative charge. So when it forms that covalent bond, it is essentially losing an electron, but if it's starting with a negative charge and it loses an electron, then it ends up being neutral. In all of the other examples, we had something positive on the left and we need to end with something positive on the right. But in this example, I've got something negative and something positive on the left-hand side. Those two charges effectively cancel each other out, and on the right-hand side, I have got a neutral product, and that's what your product should look like. The one at the end, I've got the same thing. I've got a negative chlorine and I've got a positive carbocation. Again, those two charges effectively cancel each other out, and I end up with a neutral product. And again, chlorine is using its lone pair to form a new bond with that carbocation. Right, so as well as using the electrons in a lone pair to create a new bond, you can also use the electrons in a bond. And we have seen this already in the electrophilic addition mechanism of alkenes. So here I've got a curly arrow starting at the double bond and ending at my H+. And again, this doesn't mean that the two electrons in this bond are both going to go to hydrogen, because if I did that, if I took two electrons away, I'm just going to number these 1, 2, and 3, then carbon 2 would be losing its electron and would end up with a positive charge, and carbon 1 would also be losing electron and would have a positive charge, and then hydrogen would gain 2 electrons and end up with a negative charge. Again, this is not going to happen. That would be incredibly unstable. So it doesn't mean that both electrons from the pi bond go to hydrogen. Instead, it means that the electrons in the pi bond are used to create a new bond with hydrogen. So there are obviously two carbons, carbon 1 and carbon 2, that have a share of the electrons in this bond. Okay, so this is different to what we saw over here. Over here, the electrons that I was using to form a bond were nitrogens, one atom and one atom only. Over here, the electrons I'm using at the moment are being shared between two different carbon atoms. So what's going to happen is that these two electrons are going to be used to form a bond. Let's just say carbon 2 keeps both of the red electrons and uses them to form a new bond with hydrogen. Okay, so if carbon 2 forms a new bond with hydrogen, then carbon 2 still has a share of the electrons. Carbon 1, on the other hand, does not. Carbon 1 ends up with a positive charge. And remember, it's positive 1, not positive 2, because of those two red electrons, only one of those electrons originally belonged to carbon 1. The other one came from carbon 2. So carbon 1 is not losing 2 electrons because one of the electrons was never its to begin with. So that's one potential product. Your other option, because both of these carbons, are, well, they're not exactly the same, but you do have another option. The other option is that carbon 1 gets to keep the electrons and it forms a bond with hydrogen. And in this case, carbon 1 forms a bond with hydrogen, and that means carbon 2 is losing its electron and ends up with a positive charge. We've got two different intermediates there, and we've seen that in these electrophilic addition mechanisms. So have a go at this one yourself. Similar situation, draw me the two potential products that you could get from this reaction. So this is the answer that you should have gotten, okay? Just double check that you haven't dropped a carbon. You're supposed to have 1, 2, 3, 4. Make sure in your answer you've got 1, 2, 3, 4. And again, if I label these carbon 1 and carbon 2, one option is that carbon 1 forms a bond with bromine, carbon 2 gets a positive charge. The other option is that carbon 2 forms a bond with bromine, carbon 1 gets the positive charge. Okay, so we've had a look at using a lone pair to make a new bond and using electrons in a bond to make a new bond. We're now going to have a look at using curly arrows to show breaking of bonds. So again, we have seen this in some of the mechanisms that we've looked at. Here I've got bromine bonded to bromine, and that covalent bond between them represents a pair of electrons, and I've got a curly arrow showing that the electrons are going from the bond to one bromine and one bromine only. So this is an example of heterolytic fission. The bond is breaking and both electrons go to one bromine. This bromine here is losing the electrons. It ends up with a positive charge. The other bromine gains the electrons and ends up with a negative charge. And again, it's not positive 2 and negative 2. This bromine only contributed 1 electron to the bond, so it only has 1 electron to lose, so it's positive 1. And here, yes, bromine takes both of the electrons, but one of the electrons was already its electron to begin with, and then it gets 1 electron from this bromine here and ends up with a negative charge. The next example, very similar. Press pause and have a go for yourself. So again, if this bond were to break, you'd end up with H plus and you'd end up with H minus. So you do still have neutral. You've got something neutral on the left-hand side, positive, negative on the right. So overall, you do have a charge balance. And when you're breaking a covalent bond by heterolytic fission, you do always end up with oppositely charged ions. The next one is a little bit harder. Definitely press pause and have a go at this. So I've got a carbon double bonded to the oxygen, and I'm moving the electrons from the pi bond onto the oxygen. So what is your product going to be? Press pause. So this is what your product is going to look like. Yes, you are breaking the carbon-oxygen bond, but you're only breaking one of the two bonds. This other bond here, the single bond, does not break, so the carbon is still attached to the oxygen. The two electrons in the pi bond go onto the oxygen, so oxygen gets a negative charge, carbon then gets the positive charge. So it's the same as what we've done here, but because it was originally a double bond, that carbon and oxygen are still attached. Have a go at this last one, which is something similar. All right, so I'm just going to finish this one off, okay? Again, I have a double bond here, and I'm only breaking one of those bonds, so my ring still is intact, but the two electrons that were shared between, let's call them carbon 1 and carbon 2, are now both on carbon 2. So carbon 2 is going to have a negative charge, and that means carbon 1 is going to have a positive charge. This doesn't happen in practice, okay? We're just using it as an example to show how arrows can be moved. All right, for the rest of the examples, we're going to try and put all of this together. The examples are going to start off relatively okay, and then they're going to progressively get a lot harder. So do make sure you press pause and have a go at each one. This first example, you've got two arrows. Try and follow them and draw the product. Press pause and have a go by yourself. All right, so what this shows is that this carbon here is using its lone pair of electrons to form a new bond with a delta positive carbon. In order to form a new bond with this delta positive carbon, one of the old bonds must break, and this arrow is showing me that it's the carbon-chlorine bond that breaks. That means I'm still going to have my three carbons, 1, 2, 3, but on carbon 3, I'm now going to have the CN group. The chlorine is going to leave. So this carbon forms, call those the red electrons, forms a new bond with this carbon here, and the chlorine bond breaks. Again, I need to have charges that balance. I've got something negative on the left, I need something negative on the right. So where is that negative charge going to go? That carbon is using both of its electrons to form the new bond, so it's losing an electron, so it doesn't have a charge at the end. This carbon here, the delta positive carbon, it gains an electron from the Cn minus, but then it loses an electron to chlorine. So overall, it's not going to end up with a charge, but it's the chlorine here. When that bond breaks by heterolytic fission, both electrons go with chlorine, and chlorine ends up with a negative charge. Right, have a go at the next example. Very similar, but pay attention to your charges. Here, I had something negative at the start. Here, I do not have something negative at the start, so pay attention to your charges when you have a go. All right, so this is the start of it without the charges. Nitrogen uses its electrons to form a new bond with carbon. To form a new bond with this carbon, the old bond must break, and the arrow shows me that it's the carbon-bromine bond that breaks. So I get the NH3 substituting in, the bromine is substituting out. In terms of charges, nitrogen is using both of its electrons to form this new bond. So these electrons here both come from nitrogen. Nitrogen effectively loses an electron. It ends up with a positive charge. The electrons in this covalent bond both go with bromine. Only one of the electrons was its to begin with, so it's gaining an electron, and it ends up with a negative charge. So I've started off with something neutral, and I've ended something positive and negative. But again, there's balance of charges on both sides of the equation. Right, here's the next one. Press pause, have a go with this one. So this is what your product should look like. You still have 4 carbons, 1, 2, 3, 4, and this carbocation here is now bonded to the nitrogen. The nitrogen is still bonded to all of its hydrogens. And because I've got a positive charge on the left, I need to have a positive charge on the right. That is going to be on the nitrogen, because nitrogen contributes both electrons to that new covalent bond. Right, have a go at the next one. When you're drawing this, even though I've got skeletal, do draw the hydrogen. Show yourself where the hydrogen is going. Follow these 2 arrows, see what product you get. Remember, you're starting with something negative, so you do need to end with something negative. Okay, so this is what it should look like. You are breaking the double bond between the carbon and the oxygen, but you still have a single bond holding them together. So that carbon and oxygen are still bonded. And now this new hydrogen has come in here and formed a bond with the carbon as well. Both the electrons in this new bond have come from hydrogen, so hydrogen is effectively losing an electron, so it loses that negative charge. But here, both of the electrons that were in this carbon-oxygen bond both end up on oxygen. Oxygen gains an electron, and oxygen ends up with a negative charge. So I started with something negative, and I'm ending with something negative. This next one is something similar, so again, have a go. So again, I've drawn out the product. Again, you've got a double bond. You're only breaking one bond, so carbon and oxygen are still bonded. Just make sure here when you're drawing the CN, that lone pair is on the carbon, not on the nitrogen. So you need to show that it's the carbon bonded to the carbon, not the nitrogen. If you wrote it the other way around, you wrote NC, you would be wrong. Again, I've got a negative charge here. I need to have a negative charge on product. And again, it's going to be on the oxygen. The next one I'm going to do is actually what happens. Oh, no, wait. Did I have a C? Oh, sorry, there's supposed to be a Cl there. Apologies, the Cl is supposed to be there. So what actually happens next in this reaction mechanism, because this is unstable and it's an intermediate, is these electrons go here and this goes here. So see if you can follow the two new arrows that I've just drawn and draw me the product. So well done if you got this one, because there's a bit going on, okay? The two electrons, so I could have drawn a lone pair there either. I can start an arrow from a lone pair or from a negative charge, but the electrons that are on that oxygen are going to come down here and reform that double bond between oxygen and carbon. So when you see the electrons, when you see the arrow ending on the bond between two atoms, that means you're forming a bond between those two atoms. If those electrons were going purely to carbon, the arrow would have to end at carbon. That's not what's happening here. So I'm reforming the double bond, and in order to reform that double bond, the carbon-chlorine bond has to break because carbon can't have more than 4. When the carbon-chlorine bond breaks, chlorine leaves, and it leaves with a negative charge. So I end up with a negative intermediate, and I'm ending up with a negative product. So overall, that negative charge is being conserved throughout. All right, have a go at this one. Press pause and have a go. Okay, so this here should be your answer. Oxygen is using its lone pair to form a new bond with hydrogen, but for hydrogen to form a new bond, it then breaks the old bond. So this becomes an alcohol, pulls off one hydrogen, and the electrons that were in this bond then move on to oxygen. If you look here, I start with something negative and something positive, and at the end I've got neutral products. So the positive and negative cancel out, and I end up with neutral products. Because both of those electrons end up in oxygen, it's able to lose its positive charge because it's effectively gaining an electron. I've got two here for you. There's two separate ones. There's a positive charge on that oxygen, so what are you going to get there? There's also a positive charge here on the nitrogen, so what are you going to get there? Press pause and have a go. So here are your answers, all right? You're breaking this carbon-oxygen bond, and both of the electrons are going with oxygen. So oxygen loses its positive charge, but the carbon will gain that positive charge. If we've got something positive in the reactants, I need to have something positive in the products. And make sure you don't end up losing or gaining a carbon along the way. You should only have 2 in your product. Here I've got 3 carbons in my reactant, so I've got 3 in my product. Again, that bond is breaking. Nitrogen takes both of the electrons, so nitrogen loses its positive charge, but carbon is going to gain. Again, positive in the reactant, positive has to be conserved in the products. So this next one should look pretty familiar. We'd look at it anyway in electrophilic addition, so press pause and have a go. So there are 2 intermediates here. I've just drawn one of them. The electrons in this double bond belong to carbon 1 and carbon 2. So what's going to happen is that either carbon 1 or carbon 2 are going to get the bromine. I have given the bromine to carbon number 2. That means carbon number 1 gets a positive charge. That bond there between the 2 bromines break, and I end up with a negative charge. So I end up with, start with 2 things that are neutral, but I end up with something positive and something negative. Overall, the charges balance. Make sure when you're drawing this that you don't drop a carbon, okay? Common mistake here is students draw this, okay? I have got 6 in the ring and 1 here is a methyl group. I've got 7 carbons in my starting material. If I do it like this, I only end up with 6, so that is incorrect. If you drew the other intermediate, you would have the bromine here, but you should still have carbon coming off as a branch. I'm just going to move on to my iPad now so I can show you more at the same time. They get trickier from here, but try and follow the same processes. Have a go at doing 15, 16 and 17 and then press play when you're ready to see the answers to all three. So these ones I'm just going to do kind of bit by bit rather than just writing up the whole answer. So what I've got here is I've got my OH using its electrons to pull off that hydrogen. So oxygen is going to form a new bond with hydrogen. And when it forms a new bond with hydrogen, one of hydrogen's old bonds breaks. So what that's going to leave me with then is I'm going to have my organic product, okay, which now only has one hydrogen there instead of two, and I've got H2O. In terms of charges, I have something negative, so that negative charge needs to go someplace, okay? Oxygen is using both of its electrons to form that new bond, so it's losing an electron and it loses the negative charge. But both of the electrons in this hydrogen-carbon bond end up, if you follow the arrow, on that carbon. So they sit on that carbon as a lone pair. One of the electrons belongs to carbon, but the other one belongs to hydrogen. So carbon is gaining an electron and carbon ends up with a negative charge. And then the next bit here is an extension of what would happen next. So carbon's not particularly stable with a negative charge. The electrons will then move. And when they move, again, if you just follow the arrows, okay, there's no arrows down here, so I'm just going to draw this as it was. The electrons move in between the, so, no, don't do that. I'm going to call this carbon 1 and this carbon 2. The electrons are moving in between carbon 1 and carbon 2, which tells them forming a double bond between carbon 1 and 2. In order to form that new bond to carbon 2, one of the old bonds to carbon 2 must break. And that's that carbon-oxygen bond that breaks, and the electrons move on to the oxygen. So I have a negative charge at the start, I need one at the end, and it's the oxygen that is going to get the negative charge. The electrons are basically moving from the carbon, essentially onto the oxygen. The next one here, if I look at what's happening, so I'm going to draw out the kind of general skeleton, and I've got my OH here. The electrons are moving from the oxygen to the space between oxygen and carbon. That tells me that I'm forming another bond between oxygen and carbon, so now that's a double bond. That hydrogen doesn't break, okay, so it's still going to be there. There'd have to be an arrow showing the hydrogen was breaking if it was. Originally, I had a positive charge here on this carbon. But what happens is the electrons move. I'm going to number these as carbons 1, 2, and 3. And the electrons move from between carbon 1 and 2 to between carbons 2 and 3. Okay, so carbon 3 it had lost an electron, but now it is after gaining an electron. So carbon 3 is not positively charged anymore. Carbon 2, originally had a double bond with carbon 1, but now it's got a double bond with carbon 3, so net electrons are still going to be the same. But that positive charge does need to go someplace. And if you look right at the start of the first curly arrow, it's oxygen that is using both of its electrons to form a new bond. It's oxygen that gets the positive charge. So again, I start with something positive, I end with something positive. I do appreciate that these are getting a little bit harder. So bear with me. Have a go at 18 and have a go at 19. So press pause and have a go at 18 and 19. All right, so have a look at 18. I still have the general skeleton, okay? And I'm going to number these as 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And the electrons are moving from between carbon 1 and 2 to between carbons 2 and 3, and between 3 and 4 to between 4 and 5. Initially, I had a positive charge on carbon 5. That positive charge is not going to be there anymore. Instead, that positive charge is going to be on carbon 1, because it's carbon 1 that had a double bond in the reactants and it doesn't have a double bond in the products. Okay, all of the other carbons remain the same, so that's the one that's contributing the electrons. I know 19 looks really hard, but it is essentially the same. So it's what's called a heterocycle when you've got a nitrogen, or just an atom other than carbon, in the main ring. Double bond O. Okay, and if I look at what's happening, the electrons that were in the nitrogen lone pair are now being used to form a double bond between nitrogen and carbon, so the electrons are moving in between that space. And in order to form a new bond between nitrogen and this carbon, the bond that did exist, the double bond between carbon and this nitrogen, must break, and both of those electrons go onto the nitrogen. So what I need to add here is I need to add charges. So this nitrogen here is effectively losing an electron, and then this nitrogen here is effectively gaining an electron. So I start off with something neutral, I end up with something positive and something negative, because that double bond between that carbon and nitrogen is now broken. I've got some more that look quite similar. So there's 20 and there's 21. I know these are getting a little bit harder, but you know, technically they could ask you, and they do sometimes ask quite tricky examples of these. If you are finding them really hard, though, don't get too discouraged. The longer you spend doing organic chemistry, the kind of easier this becomes. A lot of it is just down to experience, but have a go at 20 and have a go at 21. Press pause. All right, so if I do 20, okay, again, when I'm drawing this initially, I can just draw in most of this kind of unchanged, that double bond NH2. There's no arrows coming out of it, so I know it's not going to change, all right? But the negative charge here, I've got the lone pair of electrons are moving from sitting on this nitrogen to in between this nitrogen and carbon. So I must now have a double bond between that nitrogen and carbon. And because both of those electrons are being used, that negative charge is going to disappear. It's not going to be on that nitrogen anymore. And in order to form that new double bond with carbon, one of the bonds in the carbon must break, and it's the carbon-oxygen bond that breaks, and the electrons move on to the oxygen. So oxygen ends up with a negative charge. So I've still got positive, negative, positive, negative. It's just now the negative charge on the oxygen. If I look here at the next one, so I've got a ring. Again, those electrons are moving down to form a double bond between the oxygen and the carbon. In order for that to happen, the electrons in this bond are moving onto one carbon. And because both of those electrons move onto this carbon, that carbon's going to end up with a negative charge. Now, I can't go from something neutral to something negative. There has to be an overall balance. So if I have a negative charge, I must have to have a positive charge, and that positive charge will be on this oxygen here, okay? Because it's after sending its electrons into the ring, it's lost an electron. The ring, and specifically this carbon, has gained that electron. There are only 4 more. Have a go at 22 and 23. Press pause. So I've just started drawing this one out, okay? So these 2 bonds I can fill in straight away because they're not changing. And then here I've got the electrons moving from this carbon back into this space. So I'm forming a double bond there. In order to form a double bond, the double bond that was to oxygen is going to break. So I started with a negative charge and a positive charge, and I now end up with something neutral. This carbon was negative, but it's after losing an electron, because it donates both electrons to that new bond, so it's not negative anymore. And then this oxygen was positive, but when the electrons move back onto that oxygen, it gains an electron and no longer has a positive charge. So that's what that one's going to look like. And the one down here with the nitrogen, so I've just again drawn out the shell. So this oxygen here is a negative charge. It uses the lone pair of electrons to form a double bond between nitrogen and oxygen. In order for that to happen, the electrons that were in this double bond move on to this oxygen. So I end up with oxygen and a negative charge there. The nitrogen itself still has 4 bonds. The nitrogen is still going to be positive. So it had lost an electron, so it initially gains those electrons when this covalent bond forms, but then it loses them again straight away. So overall, the nitrogen stays with the positive charge, but the negative moves from one oxygen to another. This last one, we'll zoom in on this one. It looks like there's a lot going on here. There is a lot going on here. Oh God, that's actually probably too hard. Ignore that one. We'll ignore that one. Have a go at this one. Again, this also looks difficult, but see, I would, do you know what, I'm going to give you a hint. I would say number these 1, 2, 3, 4, 5, and 6. Number those 6 carbons and have a go. Right, so I'm going to just finish off this last one. Okay, I've got carbon 1 bonded to carbon 2, bonded to carbon 3, bonded to carbon 4. And you can see, I'm just going to number those again for myself. 1, 2, 3, 4. And I can see that the electrons between carbon 1 and 2 are now being used to form a bond between carbon 1 and carbon, actually I'm going to draw as carbon, right there, between carbon 1 and carbon 5. Carbon 5, I can see, is joined to carbon 6. And then carbon 6 is using the electrons that were in that double bond to form a new bond with carbon 4. So I end up forming a ring. Okay, so the electrons that were between 1 and 2 are now between 1 and 5. The electrons that were in the double bond between 5 and 6 now exist between 6 and 4. And then the electrons in the double bond between 3 and 4 now exist between 2 and 3. So you end up, sorry, that's so ugly. I'll just draw it pretty. And you end up with a 6-membered ring, cyclohexene. So that's no better. Anyway, that is your final product with 6 carbons in a ring. I appreciate that some of those are a little bit tricky, but they can ask difficult questions on this. It will become easier by the time you're at the end of year 13 and you've got exposure to more mechanisms, and this stuff starts to become a little bit more natural. But it's never something that's explicitly taught in any chapter. So it is hard to kind of get the practice you need. Rewatching this video and trying to do all of them again in a few weeks' time once you've forgotten them would be really good practice, just so you can get your head around what the arrows mean. If you can follow the arrows, it will make your life a lot easier and enable you to do some of those really tricky questions that potentially you wouldn't be able to do otherwise.